Hello friends, welcome to my channel. Let's have a look at the newly appeared problem 2421, number of good paths. So in this video, we are going to share a solution based on UniFind or disjoint set abstract data type. So here the goal is to explain why UniFind is very natural to this problem. First, I'll read through the statement of the problem to digest the requirement, and then we do a simple analysis, and finally we share a format of code. First, let's look at the statement. So there is a tree consisting of n nodes numbered from 0 to n-1 at exactly n-1 edges. So we are given a zero-indexed integer array called values, so of length m, where values I denotes the value of the ith node. We are also given a 2D integer array called edges, where edges I contains two nodes, AI and BI, denotes that there exists an undirected edge connecting nodes AI and BI. So next is the definition of a good path. So a good path is a simple path that satisfies the following conditions. First, the starting node and the ending node have the same value. Second, all nodes between the starting node and the ending node have values less than or equal to the starting node if we have intermediate node. So the problem asks us to return the number of distinct good paths. So here is a note. Note that a path and its reverse are counted as the same path. For example, 0, 1 is considered to be the same as 1, 0, and a single node is also considered a valid path. So here are three examples. So let's look at example 1. So in example 1, so the return is 6. The reason is that there are 5 single node paths. So because we have 5 nodes, and there is a good path with ending 3, so value 3, for example, this one. So the path is from node 1 to 0 to 2 to 4, right? So that's the example 1. So similarly, we can analyze example 2. So there are 5 single node paths, and so this 3, 2, and 0, 1 are another 2 good paths with end values 2 and 1 respectively. So this is example 2. Example 3 is sort of edge case. So let's look at the constraints. First, the number of nodes n is bounded above by 3 times 10 to the power 4, and the values are between 0 and 10 to the power 5, and there are n-1 edges, because here we are considering a tree data structure. So each edge actually contains, there's no self-edge, in other words, so AI does not equal to BI. So the edges represents a valid tree. So this is the statement and also the assumptions for the problem. So with that said, now let's look at the analysis. So I guess here the challenge for us is to explain clearly why UniFind is natural for this problem. Actually, the implementation is sort of routine. So first, let's look at the main idea. So here, first we need to notice that single node is considered a valid good path. So to take this part into consideration, so we just need to add the number of nodes in the tree to the final result. So below, we only consider good paths of length greater than 1. So the idea actually is simple. Actually, I would say sort of brute force. So we say brute force, but when we do the implementation, there are some tricks. So for each unique node value v, so we try to find the number of good paths with the two ends being nodes with the value v. Then we just need to sum all the good paths with different unique values. That's it. So that's the overall guiding principle. So notice that the above path the above talks about the good path with length greater than 1, right? So because for good path of length 1, it just need to count the number of nodes. So actually the count is very simple in this problem setting. So for a tree, so with a maximal node value, say v, and the key of the nodes in the tree have value being v, then the number of good paths with the two ends value being v is nothing but we choose 2 out of k, right? That is k times k minus 1 divided by 2. So here division is integer division. So why this counting is correct? So you can think of 2 things. First, by the problem requirement, the order is not important, right? So this is the one thing. Like 0, 1 and 1, 0 are the same path. So secondly is that the tree abstract data structure is also very important here. So there must exist a valid path between any 2 nodes in the tree, right? So actually there is unique simple path between any 2 nodes. So that's why we have this counting, right? So this is the main idea and the counting. So now let's look at the walkthrough. So for the walkthrough, so we just make it fast. So for example, let's look at example 1. So the largest value in this tree is 3, right? So we have 3. So we have 2 3s, right? So then the number of good paths with 2 ends being value 3 is 2 choose 2, that is 1, right? So if we look at the next largest value, that is 2. So for the value 2, so in the path we can include values node with values 1, right? Smaller than 2. So in this subtree with 0, 2, and 3, the number of nodes with value 2 is 1. So actually there's no good path with 2 ends being 2. So here again we talk about a path of length greater than 1. So for the smallest value 1, so there we have 0, we have 3 here. So because we cannot include larger values in the path, so these 2 parts actually form 2 connected components or 2 subtrees. So the number of good paths with length greater than 1 are 0 respectively. So this is 0 plus 0, that is 0. So the total number of good paths in this example 1 is nothing but 5. So this is the length 1 good path plus 1. So one of the good paths with ends being value 3 and plus 0, 0, that is 6. So that's a walkthrough for example 1. So similarly, you can check example 2. So now with that done, so let's look at the procedure. So the procedure actually, for the procedure, we want to emphasize 2 points. First, if we examine the above procedure, so we shall build the tree from nodes with smaller values. So in other words, we compute the number of good paths with smaller values in the 2 path ends. So what's the reason? So because the good path can contain middle nodes with values smaller than path end value. So if we start from the largest, so actually we directly build the whole tree for the single largest value in the tree only, right? So that's the order. So once we realize the order, so why we use UniFind, so why it's natural. So actually, this is also easy to understand because when we examine a value v, so to compute the number of good paths with 2 ends having this value v, so the nodes with value v might be not connected, right? So we need to use UniFind to dynamically monitor the clustering when we look at v values from small to large. So here, in order to better understand this point, let's look at one scenario. So for example, if we have a tree with root value 100 and left subtree with node values 10, 7, 7, 10, 10. So I put 3, 10 here on purpose. And then the right subtree has node value 10, 2, and 10. So now if we want to look at the number of good paths with length greater than 1 and 2 ends being value 10, what do we do when we do the computation? Because this left subtree and the right subtree are disconnected due to the value 100, because 100 is larger than this value 10, right? So the number of good paths is, so in the left subtree we have 3 10s, so we can choose 2 out of 3. And then in the right subtree we have 2 10s, so we can choose 2 out of 2. So that is 3 plus 1 is 4. So in this case, so we have 4 good paths of length strictly larger than 1 and 2 ends value being 10. So the reason here we have 2 components is due to the separation by the root value 100. So however, if the root value is less than or equal to 10, for example, let's say 5, then actually the 2 components are merged, right? So we have 5, that's the root, and then the left subtree and the right subtree. So in this case, how many good passes of length greater than 1 and ending with 2 ends value being 10? That is, choose 2 out of 5. The reason is that, so this in this component, so any 2 nodes are connected. So we have 5 10s, and we just need to choose 2 out of them. So this number is much larger. So because this is 5 times 4 over 2, that is 10. So again, so in order to emphasize this is a dynamical in nature. So notice that if the root value remains 100, but if we consider computing good paths with end value being 100, so we have only one connected component again, the whole tree. But in that case, because we have only one 100, the good path with 2 ends being 100 is 0 because we have less than 2 nodes with value 100. So that's the analysis. So now the plan for this problem is the following. So we are going to implement the union find abstract data type. So here actually there are 2 choices. So we can do the implementation as a separate class or inside the function. So here I'm going to make it inside the function. So because for presentation purpose, we want to write some details, right? Not pursue for the shortest code. So actually, there are quite a number of such implementations in our channel specific to different application cases. So secondly, we are going to use this union find to solve the problem here. So with that said, let's look at the code. So I hope that with the above explanation, the logic should be clear. So now let's divide this solution into different parts. So I'm going to use union find. So first, I'm going to build this graph. So second, I'm going to find the value at nodes mapping. And thirdly, so I'm going to implement a union find helper functions. And lastly, so we write up with the problem logic. So if we split this whole code into pieces, so then actually the implementation becomes very easy. First, let's build the graph. So I'm calling this graph G. So here I'm going to use collections default dictionary. So I'm going to choose, let's see, default dict. So I'm going to choose the container as a set, right? Then we're going to iterate over the edges for ig in edges. So what we're going to do is that we add the node to the adjacent list of node I, and similarly we do the reverse. G of G add I. The reason we do this is because the edge is bidirectional or undirected. So this is the part 1. So we build this graph so that we can track the neighbor relations. So this is the first part. So the second part is that we want to find the unique values. So I'm going to have, I call it nodes. So collections. So default dictionary. Again, I'm going to use that. So this time I'm going to iterate over the values. So for I we enumerate so values. So the I will be the node and V will be the value. So we're going to do this nodes. So this is the unique value V, and then we add the I. So in other words, we partitioned all the nodes according to their values. So this is the second part. So the third part will be the implementation of UniFind, which is very straightforward. So first, I'm going to track the length of the values so that we know how many nodes we have. Maybe we want to track. And then we're going to initialize two lists. Actually, we can use dictionary, right? So let me use a list here, just for I in range M. So, and also we want to use a rec. So here the rec will be the size. So initially it's 1 for I in range M. So this finished the preparation. Now let's do the hyperfunction find. So here I'm going to write it in a recursion format. So it's much easier. So if parent I is equal to I, then just they need to return I. So let's also maybe return parents. That's the same. Otherwise, we're going to reset the parent of I to be find parent I. And then what we are going to return is nothing but a parent I. So this is the find. Also, we need a union. So actually, a vanilla union will be fine. But now let's write a union function with union by size or by rec. So union, so it accepts two nodes ij. And then what we're going to do is that first we're going to use the find method. We implemented find I, find j, right? Then we check the size. If size of root 1 is no less than size of root 2. In this case, so we're going to set the parent or the root of root 2 to be root 1. And then accordingly we increment the size of root 1 by that of root 2. So this is the one case. In the other case, so actually we just need to do the reverse direction. So we set the root 1 of the parent to be root 2, and then we increment the size of root 2 by that of root 1. So this is the union operation. So with that said, we finished the first three parts. Build a graph, find a value and nodes. So basically here we partition the nodes according to the unique values. And then we implement a union find hyperfunction. So that's about it. So the three parts are actually all very straightforward. Now let's look at the problem logic. So here I'm going to initialize the answer to be n, because this n counts the n single node good path, right? And then we're going to do the tree build procedure or iteration. So for v in sorted nodes case. So this sorted means that we look at the value from small to large, and then we're going to consider add nodes with value being v, right? So for I in nodes v, so these i's are the values are the nodes with value being v, right? So now what we are going to do is that, so for j in the neighbor of this node I, for each of the nodes, so then if values j is less than or equal to value v, so values I, so actually this values I is nothing but v. Let's first keep this, and then if this is the case, we are going to do union operation. So union ij, right? So this is the main step, and then we're going to count the node with value v in each of the components. So here let's first initialize a counter. So it's collections default dict, so going to be int, and then for I in nodes v. So in total we have, if the nodes v have n nodes, so we want to distribute this n node or check this node in different subtrees, right? So assume that we have 10 nodes, maybe 5 are in that in one subtree and the other 5 in another subtree, right? So that's the purpose. So then we are going to find the representation of the cluster connected component or subtree, and then increment that count by 1. So this find I, or this root, is a representation of that subtree, and then this increment by 1 is count a one instance of node with value being v, right? So this is the case. Then afterwards, after we done this, so what we are going to do is that for each of the subtree in the count, so we are going to compute how many good paths do we have. So with two ends being value v, and length is at least 1. So for x in count values, then the answer will be incremented by, so we choose 2 out of this x, right? So that is x times x minus 1 divided by 2. So notice that if x is 1, so this is still okay because this is 0, right? And then that's all the main logic. Then what we need to do is just return the final state of this answer. So with that done, let's first do a special case check. Yeah, it passes one special example. Now let's look at another test. Yeah, it passes all the test cases. So here actually there are different counting procedures. For example, here also notice that the value is I. So because I is in node v, so this is always v. So we can actually replace this by v and then do the check again. Yeah, it's still okay. And this is one thing we want to emphasize. Another thing that is another format of doing the counting. So we can actually set the answer to be 0 at the very beginning. So when we have this number of nodes, so we can do the count like this. So we add x, we count the good path with just one node and the value being the v, right? So this is also okay because here we set it to 0. So this x, if we sum them up, so this will be n, the number of nodes. So let's do a check again. Yeah, it also passes the test. So let's change back to here is n, because we actually first counted all the single node path, and then here let's do not add this x. So that's a solution format for this specific problem. So let me give a quick summary. So here the thing or the technique we used is unifind, and 2 points to notice are that first, so this unifind is actually very natural, and secondly, the data structure or the tree data type is also very important, because in the tree, choose arbitrary 2 nodes, there is a unique simple path in between. So in the specific implementation, actually what we do is based on this idea. So this is actually very simple. So for each unique node value, so we find the number of good paths with the 2 end being nodes with value v. So then we just sum up all this paths across all the unique values. So with that said, I guess that's about it for this video. Thank you very much.